Uh, Hello, good morning. So today we are going to start topic number 9, which is chapter 5 of the textbook. So this is about the compacting and finishing. So this topic connects with our previous topic in a way that we have also considered about the one of the condition of the soil, which was the compacted condition. So we had the bank condition of the soil, which is excavated, and we had the loose condition of the soil. So can you hear me?
Yes.
Hello, can you hear me?
Yes, we
Is
can.
everyone here? Hello?
Yes, we hear you.
Okay. All right. So compact. The third condition which we discussed about was the compacted condition. So the soil which was in the bank condition, that is in its natural state, that soil was excavated. Then the soil was transported, and in that condition, the soil was in the loose condition. And then that transported soil is now placed, and then that soil is compacted. So compacted is compaction of the soil means to need to clear my throat. Yes. I resume the recording. So for understanding the compaction, so first of all, let's understand the principles of compaction. So the compaction process is the process of increasing the density of soil by mechanically forcing the soil particles closer together, thereby expelling air from the void spaces in the soil. So you remember that a soil has three types of materials: the solid particles, the liquid, that is the water, and the air. So compaction is the removal of the air between the soil particles. So thereby the soil particles come closer to each other. Whereas the removal of the moisture from the soil is a process which is called as the consolidation. So there is a difference between the consolidation and the compaction. So compaction should not be confused with consolidation, which is an increase in the soil density of a cohesive soil resulting from the expulsion of water from the soil's void spaces. So the consolidation process takes place in the cohesive soils, mainly takes place in the cohesive soils, where the water is removed from the soil, and as a result, the soil consolidates. And it is consolidation is much slower than the compaction process, and it's like more a natural process, whereas the compaction is a process which is driven to the soil. Okay, so therefore we mechanically bring the particles of the soil closer with each other. By in that process, the air is removed, and then the soil is compacted. So the compaction has a number of benefits to the soil, and compaction is a very important process because it is due to the compaction that we get the increased bearing strength of the soil. We get the reduced compressibility of the soil. The volume change characteristics of the soil are improved, and we get the a reduced permeability of the soil. So all of these are the desirable properties of the soil, which we obtain as a result of the compaction. So compaction on a building site is different from heavy construction. The compaction is needed in almost all civil engineering construction projects, not only on the building site, but also on the heavy construction projects. But the compaction on the building site is different from the heavy construction because of the limited differential settlement that can be tolerated by a building foundation. So on a building foundation, there is a requirement that the settlement, the differential settlement should be as minimum as possible, because if there will be a high amount of differential settlement, then it means that the building on one side will settle more than on the other side, which may have the detrimental effect on the building. So we have to control the compaction on a building site very carefully, so that we can be sure that the compaction at different areas on the building site is uniform. So not only the total settlement have to be controlled, but more importantly, the differential settlement have also to be controlled. The settlement is, I think you may have understood this term from your geotechnical or soil mechanics courses. So in soil mechanics course, this is a very important terminology about the settlement, and of course even the compaction and the bearing strength and the other terms. So we are using many soil mechanics or geotechnical engineering terms in this topic. The necessity of working in confined areas close to the structures is also quite important in the case of the building site, because we cannot produce a lot of vibration in those confined areas. If a lot of vibrations are produced in those confined areas, those vibrations may affect the neighboring buildings as well. So it's a very controlled process of compaction, which may needs to be performed on the building site. The smaller quantity of the earthwork involved, of course, compared with the heavy construction, like such as the construction of the dams, construction of the highways, the site on the building is relatively smaller. So a smaller quantity of the earthwork may be involved. And accordingly, the equipment that will be used for the compaction on the building site will be also different. So for understanding the principles of compaction, we need to understand about the moisture content in the soil, because the compaction in the soil depends very much about on the moisture content on the soil. Of course, in the definition of the compaction, we have said that it is the removal of the air content in the soil. Removal of the air content from the soil, that is the removal of the air, so that's why the particles comes closer. However, the measurement of the air in the soil is difficult. We can easily measure the moisture into the soil than the air content into the soil. So it has been found that if a soil is compacted, then the optimum amount of maximum amount of compaction which can be obtained in the soil depends on the moisture into that soil. So for example, if we have two samples of the soil and two different types of soil, okay, one type 1 soil, another is the type 2 soil. And these type 1 and type 2 soils will have their moistures in that, moisture in that. So if we will apply the equal amount of effort on those two types of soils, which will have different moistures, or maybe the same type of soil with different moistures, then we will obtain different type of different amount of compaction on those soils. So if we have a clay soil with 20% moisture content, and if the same soil if have like 10% moisture content, and if you apply the same type of effort in those two soils, those same type of effort will not produce the same type of compaction into those soils. So therefore, in those situations, we will say that the moisture content in the soil plays an important role in the compaction. So we call the optimum moisture content is that moisture content by which we can achieve the maximum amount of compaction. So to determine the maximum density of the soil using the Proctor test procedures, compaction tests are performed over a range of soil moisture contents. So we talked about the testing of the soil. So for if we want to determine the amount of compaction, so we have to simulate that compaction into the laboratory setting. So for that compaction, for that simulation, we perform the tests, which are called as the Proctor tests. There are two types of Proctor tests: a standard Proctor test and the modified Proctor test. So basically, in those Proctor tests, what you do is you compact the soil in different layers. So that means we take a soil sample into a steel container. You put a layer of the soil, then you apply a specific number of blows with some tamping rod or hammer onto that soil. Those specific number of blows are performed by dropping the hammer from a specified height. And similarly, layer by layer, we perform those effort. So after performing those specified amount of effort, then the density of the soil is measured. And then with that density of the soil, also the moisture content of the soil is measured. So that will be the that test is then repeated at different moisture contents, and then we plot a curve. So for each moisture content, we will get the density. So at a moisture content where we will get the maximum density, that moisture content will be called as the optimum moisture content. Okay, so first of all, let's see what are these characteristics of these two tests are. The Proctor tests are standard and the modified. In the standard test, we use 102 millimeter mold, which is the same as in the modified test. Similarly, the height of the sample is between 117 millimeter in both of the tests, but the difference comes in the number of layers. So the number of layers in the standard test are 3, number of layers in this modified tests are 25. The blows per layer are the same. The hammer is heavier in the modified test than the standard test. The diameter of the hammer is the same. The height of the drop of the hammer is also different. It is higher in the modified test. And the volume of the soil which is used into the sample is also the same. However, due to the heavier hammer, higher drop, and the more number of layers, the compacting effort is much more than the standard modified types. This is almost 4 times the modified test. It is almost 4 times the standard test. So these tests, one of these tests can be used. And when we repeat these tests for different moisture contents, so we get these kinds of curves. So for example, for the standard Proctor test, we see that when the moisture content is increased, okay, and then we also get an increase of the density. Until after that, when we get the maximum density, and a further increase in the moisture content will not further increase the density of the soil. So we will get a curve of this shape for the standard Proctor test. Similarly, we obtain a similar shape curve for the modified Proctor test. But the difference between the standard and the modified test results is that we get higher density in this modified Proctor test than in the standard Proctor test. So in both of these curves, we get a highest density at a certain level of the water content. So that certain level of the water content is called as the optimum moisture content. And here you can see that with the the optimum moisture content for a modified Proctor test is less than the standard Proctor test. So, which is obvious because we are applying more effort in modified Proctor test. So we can achieve a higher amount of density at a lesser water content as well. So it means that if we want to achieve a higher density in a relatively dry soil, so of course, more effort for decomposition may be required. Okay, so again, we also get if the test is repeated for different types of different levels of compacting efforts, we can also achieve a dotted line curve over here, which will be called as the line of optimum. So you can see that with the increasing effort, we will get the higher dryer density. The line of optimums will decrease. The line of optimums will decrease. That means we will get the higher density at a lesser and lesser optimum level. In addition to here, over there, a zero air voids curve has also been shown. This is more like a theoretical curve, which is a kind of theoretical value for which we can achieve the maximum density. So remember that these are the standard Proctor tests and the modified Proctor tests. These are the laboratory tests. So we have to simulate these efforts, these kinds of efforts in the field as well. So therefore, in the field, to achieve the similar effort, we have to perform different types of compacting equipment, and that we are going to discuss now very soon. On the other hand, what we have over here is that the different types of curves may be achieved for different types of clay. So here you can see that this curve number 1 has a very unique optimum moisture content. So the curve increases very sharply and then decreases very sharply before or after the optimum moisture content level. So this curve is for a well-graded clay sand and gravel. So this means that it is relatively easier for these kinds of sands to compact it. But on the other hand, we have this curve for number 7. So you can see that we are not achieving very high amount of density as well. And the increase in the density with the different moisture contents is also not very sharp compared with that. So what is this curve? These are called as the heavy clays. Similarly, for number 6, for lean clays, it's very difficult. And so, for number 5, if you can see that, although the density is relatively higher than the heavy clays, but with different moisture content, there is hardly any appreciable difference in the densities. So this curve is for the uniform fine sands. So depending on the type of soil, the modified Proctor test results may be different for each type of soils. So, and then these results correspond to the type of soil. So it is generally understood that the heavy clays and the uniform fine sands are relatively difficult to compared with the well-graded clays and sands. So this means that the grading of the soil also plays a very important role in the compaction. So principles of compaction specifications. So the compaction specifications are intended to ensure that the compacted material provides the required engineering properties and a satisfactory level of uniformity. So in the specifications of the project, it is normally specified that this much level of the compaction of the soil is needed. So typical density requirements range from about 90% of standard Proctor to 100% of the modified Proctor. So the specifications say that you may adopt certain tests to obtain the density values. And then based on those tests, if the densities achieved in the laboratory are if the densities achieved in these on the site are comparable with those standard Proctor test results, then the compaction may be acceptable in the soil can be acceptable. Generally, higher percentage for higher load is specified. Okay. So up to now, we have talked about the measuring the density in the laboratory, but we have also methods for measuring the field density in the measuring the field density as well. So to verify the adequacy of the compaction, the density, that is the soil or asphalt actually obtained in the field, must be measured and compared with the specified density. So one thing is the specified density. That means this much density have to be achieved. The other is the measured density. That means this much density has already been achieved. So how to measure those? Measure that density. For this, we have several methods. One of the method is the liquid test. So liquid test measures the volume of the material removed by measuring the volume of the liquid required to fill the hole. So that means in the compacted soil, a hole is made, and that hole is measured with some kind of liquid, which may not be readily absorbed into the soil. So that by the measurement of that liquid, then the density of the soil may be measured. So for example, we can find the weight of the soil removed, and then we can fill that weight of the soil removed with the weight of the liquid. So for that liquid, we already know the density of the liquid. So by the comparison of the weight removed and the weight filled in, we can measure the field density. Similarly, in the sand test, the hole is filled with the uniform fine sand. So if the soil is such that if the soil is such that it may absorb that liquid, or the liquid may not be very much readily available, or it is difficult to measure the weight of the liquid, or some difficulty when the liquid test cannot be performed. So the hole can be filled with sand instead, and then we can measure it with the uniform sand, with the density of the uniform fine sand as well. More sophisticated methods use the nuclear density devices. So these nuclear density devices measure the amount of radioactivity from a calibrated source that is reflected back from the compacted material to determine both material density and moisture content. So these types of calibrated materials, calibrated equipment gives us the measure of the density. With some safety issues involved with the nuclear density devices, there are some non-nuclear density gauges that are also available that measure the asphalt density, temperature, and moisture content. Equipment mounted compaction measurement and control systems are being offered by a number of compaction equipment manufacturers as well. So the previously those measuring tools which was mentioned are more generic for these purposes. However, the compacting equipments often are also equipped with such devices which can measure the density as well. So the equipment manufacturers can also provide some system to measure the field density, which are normally installed into the compacting equipment as well. So then what are the different types of compaction equipment? So we have various types of compaction equipment. Principal types of compaction equipment include the tamping foot rollers, grid or mesh rollers, vibratory compactors, smooth steel drum rollers, pneumatic rollers, segmented pad rollers, and tampers or rammers. So you can see that a wide range of compacting equipment are available. So the tamping foot rollers utilize a compaction drum equipped with their number of protruding feet. Okay, so there will be a compaction drum, that means in the form of a very heavy steel roller, okay, in the form of a drum, and then that drum may have some protruding feet coming outside of that. Okay, so on the other hand, there may be grid or mesh rollers that utilize a compactor drum made up of a heavy steel mesh. So instead of the protruding feet, they have the steel mesh, heavy steel mesh. The vibratory compactors are most effective in compacting non-cohesive soils. They may also be effective in compacting cohesive soils when operated at low frequency and high amplitude. So vibratory compactors, instead of providing the weight from the steel drum, they also provide the vibrations as well. So those vibrations are helpful for the non-cohesive soils such as the sands. But in the cohesive soils, it can be also used if they are used at low frequency and high amplitude. Steel wheel or smooth drum rollers are used for compacting granular bases, asphalt bases, and asphalt pavements. So we those rollers without any protrusions from the drum or without any steel mesh, they can be also used, so that they are just the smooth drum rollers. Rubber tired or pneumatic rollers are available as light to medium weight multi-tired rollers and heavy pneumatic rollers. So rubber tired rollers can be also used. And segmented pad rollers are somewhat similar to the tamping foot rollers, except that they utilize pads shaped as segments of a circle instead of feet on the roller drum. So they are similar to the protruding feet rollers, but instead of the protruding feet, they have the semicircular shapes, protrusions, which are relatively better for disturbing the surface of the soil less compared with the protruding rollers. Okay, so here we have some different types of pictures of the different types of rollers. So the smooth steel wheel roller, so that means the wheel will be smooth over here. This is the vibration roller, so self-propelled vibration. In addition to this heavy load of this wheel, front wheel, it will also provide the vibration. This one is the small multi-tired pneumatic roller. So heavy pressure multi-tires may also provide the compacting effort. And then there is this heavy pneumatic roller. So that means you can see that a very heavy weight has been there, and then that heavy weight is being pulled over there, over the surface. This is another form for the self-propelled tamping foot roller. So therefore, in this roller, we have the tampings outside, coming outside of the wheels or the drums. Okay, so these tamping efforts then provide the compaction. Self-propelled segmented steel wheel roller. So here we have the segmented steel. That means segments have been provided over here on the wheels. That means those protruding segments. So, and then the sheep foot roller. In the sheep foot rollers, so you can see that relatively sharper protrusions have been provided. And in the grid roller, steel mesh has been used on the surface of the roller to provide the compaction. So sometimes the rollers are self-propelled. That means they can be driven by the attached driving mechanism, or they can be pulled by some other machines as well. So different types of rollers are used. Here we can see that a walk behind vibratory plate roller. So this is also a compactor. This is also a compactor. So this, in this case, of course, it is quite lighter compared with those big machines, but in addition, it can provide the vibrations. So due to those vibrations, the compaction can be achieved. So compaction in the confined area. So the equipment available for compaction in confined areas, such as trenches and around foundations, include small vibratory plate compactors, dampers or rammers, a walk behind static and vibratory rollers, and attachments for backhoe and hydraulic excavators. So here we have a few more examples for the smaller scale roller. So here, this is a relatively smaller scale roller, vibratory tamping foot compactor. Okay. Another one, this is a small vibratory rammer. So in this case, this is different from the previous case over here, which was the vibratory plates. A plate is used for the vibration and compaction, but here a ramming action is used. That means it is more pointed type of action, which is applied from one point to another point. And then once the compaction is placed, compaction is provided at some point, then this equipment is lifted and then placed at some other point to provide the compaction on point-to-point basis. Another one is this compactor. In this case, this compactor is being controlled by a controller. So the operator can walk behind that roller, but the operator does not have to push that roller. The operator just have to control it by the remote control. This is a compactor which in this case we can attach the compacting wheel, the compaction wheel. We can attach it with the hydraulic excavator. So a hydraulic excavator, if modified with those instead of the hydraulic bucket, instead of that excavation bucket, we can place the hydraulic compaction wheel on that hydraulic roller, then it can also provide the compaction. Another is the vibratory plate compactor attachment for the excavator. So in addition to the vibrating wheel, a hydraulic plate can be also attached to the hydraulic excavator for the compaction. This table shows the compactors for confined areas. So some of the compactors which can be used in the confined areas, the details and the necessary data for those compactors is provided into this table. So for example, if the compactor is a rammer or a tamper, for example, like this is a rammer and this is a a tamper, okay, rammer or tamper, these kinds of compactors. The weight is normally about 49 to 107 kilogram. They provide a horsepower in about 2 to 4 kilowatt. Their frequency is from 550 to 700 vibrations per minute. They can provide a force of about 8.2 to 26.2 kilonewton, and they can work in a width of about 10 to 41 centimeters. So vibratory plate rollers can work in a width slightly higher, slightly more widths. Say, similarly, vibratory rollers may range from 10 to 109 millimeters. So different types of power, frequencies, and forces may be provided with those compactors. So depending on the area of the site, we may need to choose an appropriate vibratory roller for the job. Similarly, the excavator attachments may be also used, and then some data needed for those excavator attachments is also provided over here. Okay, so compaction equipment and procedures. So selection of compaction equipment. So the proper selection of compaction equipment is an important factor in obtaining the required soil density with the minimum expenditure of time and effort. So the chart in next figure provides a rough guide to the selection of compaction equipment based on the soil type. So if we have, say, different types of material, rock, gravel, and sand, clay, etc. So for these kinds of equipment, we have a number of choices, starting from the steel wheel, pneumatic, vibratory, tamping foot, and grit roller. And then you can see that, of course, we can see that certain type of compacting equipment are suitable for certain types. So these are represented as the recommended. Some may be acceptable, some may be marginal. So for example, steel wheel roller is recommended for the rock, gravel, clean, or silty gravel. Okay, gravel with clay gravel. So steel wheel roller is acceptable for that. But steel wheel roller is not acceptable or not very effective for clean sand or silt. Okay, silty sand or clean sand, steel wheel roller is not very acceptable. For this, vibratory roller may be acceptable, or maybe a little bit of green roller may be acceptable. So this table may be very useful to select the type of roller for the type of soil which we may have. Also, the compaction operations depend on the, of course, the type of the equipment. So the effect of moisture content on the dry density of a silty clay soil in 9-inch loose layers when fully compacted by up to 64 passes by different types of compacting equipment. So this table shows that, as you can see, that this table is similar to the one, this figure is similar to the one which we see before for the modified and the standard Proctor tests. So pneumatic a tired roller, for example, over here has been used. And you can see that for the, if we have this type of soil, that is the silty clay soil, so the effect of different types of roller on that silty clay soil has been shown over here. So here you can see that the optimum moisture content obtained for this type of soil is much closer to the standard Proctor test. But with others, for example, vibrating steel, it is much different, and then much different density has been achieved over here. For over here, we have these club foot, sheep foot roller, and then taper foot, sheep foot roller. So we achieve different types of moisture contents, which are different than their standard Proctor compaction test. So the main purpose for showing over here, for showing these curves over here, is that it is sometimes very difficult to achieve the same type of moisture content in the field compared to what we achieve in the standard Proctor test, or even in the modified Proctor test. So therefore, appropriate type of the choice and the use of the appropriate type of equipment is very important. So in this case, this pneumatic wheel tired roller may be very useful because it may provide a curve which is much closer to the standard Proctor test. Also, this curve shows that the number of passes, as we increase the number of passes of the compacting equipment, the increase in the density after, say, about 10 number of passes is much slower. So that means up to 10 number of passes, there is the appreciable increase in the density. But after the more than 10 number of passes, the increase in density is just marginal. So therefore, in order to avoid the extra effort, we have to choose such an equipment with which we can achieve the required density in less number of passes than they are required. In less number of passes than may be required by some other equipment. So because for each pass of the equipment, more time and effort will be consumed. So in order to save those times and effort, we may need to choose the correct type of equipment so that we can achieve the desired density of the soil in the less amount of effort. So then in those situations, how then we can determine the production of the compaction? So estimating the production, compactor production. So this is achieved by the this equation. If we want to achieve the compacted cubic meter of the soil per hour, so we can use this formula: 10 times W times S times L times E divided by P. Okay, so where P is the number of passes required. So that means if the more the number of passes required, less will be the compacted cubic meter per hour. That means if we need more passes, then that means we are our compactor production will be less. And when what is this? W is the width of the compacted per pass. So this means that how wide area we are compacting in one pass. So that means what is the pass? Pass is the, if pass is the one cycle, okay, of compaction by the equipment. So that equipment then moves from point A to point B. So between point A to point B, then there will be a one pass, and then the equipment may move from point B to point A, then that will be another pass. over here. So how many passes of the equipment that may be required? By this formula, then we can determine the production of the compactor. The other parameters in this formula are S is the compactor speed, so which may be given in miles per hour or kilometer per hour. But remember that this formula we can only use for the SI system of units. So for the miles or feet system of units, we have another formula. I did not put it over here. And where L is the compacted lift thickness. That means in what is the thickness which we are compacting it. Okay, so we will place a material, and then we say that we want to achieve a thickness of a compaction in the thickness of about 15 centimeter. So that 15 centimeter will be the lift thickness over here. And E is the job efficiency. So that means in 1 hour, how much is the amount of effective work. So using this formula, then we can determine the compaction. So the units are cubic meter per hour. So W is in meter, S is in meters per hour. Okay. L is L is also in meters. Okay. So yeah, so it will give the answer in cubic meter per hour. The speed, because one of these factors is the speed. So the appropriate speed have to be chosen. So that appropriate speed for different types of compactors can be chosen with the help of this table. Okay. So if it is a plate compactor, then what type of speed may be chosen? So 5 to 8, 8 to 16. So normally you can take an average of these ranges for the speed. Okay, our next topic, that was the topic for the compaction. Our next topic is the ground modification. So what is this process? So this process is the process of giving natural soils enough abrasive resistance and shear strength to accommodate traffic or design loads is called ground modification or soil stabilization. So there are various soil stabilization methods. In fact, I think this topic is is normally covered in more details in the soil mechanics or geotechnical engineering courses. But here we have these soil stabilization methods into these 4 categories: mechanical, hydraulic, reinforcement, and physiochemicals. So in the mechanical, we have the compaction method, deep compaction method, vibroflotation. So compaction, in fact, which we just described before, is in a broader sense, it's one of the methods in the which we can classify into the ground modifications. The other ground modification methods are the hydraulic, that is the drainage, preloading, electroosmosis. In the reinforcement, we have the confinement, inclusions, mini piles, soil nailing, stone columns. In the physiochemicals, admixtures, freezing, grouting, and heating. So in your textbook, some small details about these small descriptions and the details of these tests have been given over here. A detailed coverage of these different methods is not in the scope of this topic. So we will just have very brief description. So mechanical methods, hydraulic methods, reinforcement methods, physiochemical methods, granular admixtures. In the physical-chemical methods, we can consider the granular admixtures, Portland cement, and the use of lime, asphalt. So in the mechanical methods, the compaction process, as we discussed in the previous section of this topic. So it is called as the mechanical stabilization. So in this case, the additional methods are dynamic compaction or deep compaction. It involves dropping a heavy weight from a crane onto the ground surface to achieve soil densification. So it's a kind of a very scary method. That means a heavy weight is dropped on the surface. Okay, so this is called as the dynamic compaction. Typically, drop weights of about 10 to 40 tons. That means in the SI units, it is 9 to 36 metric tons are used with a drop height of about 50 to 100 feet, 15 to 330 meters to produce soil densification to a depth of about 9 meters. So this is quite a very large scale operation. That means it may produce quite a lot of noise as well when such a heavy load weight is dropped from such a height. So that may produce about a densification of the depth about 9 meters. So this type of operation can only be recommended in very open spaces where there are no nearby buildings there, because that may produce a lot of vibrations in the surrounding areas as well. So the horizontal spacing of drop points usually range from about 2 to 8 meters. Okay, 2 to 8. So at a spacing of about 2 to 8 meters, these drops are made. Okay, mechanical methods, we have the vibratory compaction, also called as the vibroflotation, and vibrocompaction is the process of densifying cohesionless soils by inserting a vibratory probe into the soil. So this is more like the one method which we have just previously discussed. Vibrations produce the compaction more effectively in the cohesionless soil, such as the dry sands. In the hydraulic methods, the water is removed from the saturated cohesive soils. So as it is done in the consolidation process. Consolidation process is more or less a natural process, but if that process can be accelerated by these hydraulic methods, that means we can remove the water from the cohesive soils. So then we can also modify the soil, and then the soil may naturally be compacted. So it is usually additional weight on the soil called the surcharge is placed on the soil. It is a long-term process. That means in those processes, the soil is very cohesive over here, and it is not very easy to remove the moisture from the soil. So that means some sort of long-term pressure on the soil is provided, and then is placed, and then with the passage of the time, the water is expelled out from the soil. So other variations in use are the sand columns or plastic drain tubes, and electro-osmosis to speed up the drainage of the cohesive soils. So that means in the sand columns, as you can see that some holes are made on those soils, and those holes are filled with the sand. The sands help to absorb the moisture from the adjoining soils. So in this case, the process of removing the moisture from the soil is improved. And also the electro-osmosis process is also used. So that means some electrical signals are placed into the soil that also help to move the soil out from the area. Okay, so the reinforcement method is it includes the confinement, inclusion, mini pile, soil nailing, and stone column. So as the reinforcement shows that it provides the external supports to the soil. That means some sort of stronger materials are inserted into the soil, and then that makes the soil more stronger. Okay, yeah, that makes the soil stronger. Of course, we are not covering very much details of this due to the scope of this topic. Physiochemical methods in common construction usage, the term Soil stabilization refers to the improvement of the engineering properties of the soil by the use of physical or chemical admixtures. So we can chemically change the characteristics of the soil by use of the chemical admixtures. So these are also available. But remember that not every kind of methods may be used in all situations. Okay, so for different situations, we may have to use some different methods where it is appropriate. So the principal physiochemical admixtures used for soil stabilization includes the granular materials, Portland cement, lime, and asphalt. So cement can be mixed into the soil, the lime, which is the calcium hydroxide based material, that can be also used. Granular admixtures. So soil blending with granular material is often used to produce a well-graded mixture without excessive fines, which is suitable for compaction. So basically, the soil is then mixed with the other materials. So then that soil which is obtained after mixing has the better grading. The effectiveness of the Portland cement as an admixture diminishes rapidly as the soil's plasticity exceeds 15. Portland cement can be also used, but if the soil is quite plastic, that means the soil can deform very well, deform quite a lot, which is measured by the plasticity index. The effectiveness of the Portland cement has been found to be not too much. So I think these types of topics are covered in more details in the soil mechanics courses. But in the textbook chapter, we have some of the more details in the regarding these topics. So you may refer to those descriptions in the textbook. Asphalt. So asphalt admixtures are generally not effective in soil having more than about 30% fines by weight or a plasticity index greater than about 10. So asphalt can be also used, but remember that this asphalt may not be very effective under these conditions. Okay, that is more than the soil may have more than 30% fines. So there are some sieve sizes by which we can measure the number of fines. That means very finely graded soil, it may not be very effective. Or in other case, if the plasticity index is greater than about 10. Granular modification. So the common stabilization materials are then this granular admixtures. So they can be used in various types of soils. Granular admixtures can be used in various types of soils. Its quantity varies. But in the Portland cement can be used in gravel, sand, silty clay, and silt. All types of soils it can be used, and it needs a curing time of about 24 hours. So it is quite quick curing time. Okay, it can be used like 3 to 4% by weight, or ranging from 6 to 8% by weight. The lime can be also used in a similar way, but lime is relatively slower material to consolidate, so it needs a curing time of about 7 days. But on the other hand, there is a quick lime as well, which settles or consolidates very quickly. So within 4 hours curing time it can be used. And then asphalt can be also used in different types of soil, in different types of quantities by weight percentages. Okay, so the last subtopic in this compaction is the finishing operation, grading and finishing operation. So the grading is the process of bringing the earthwork to the desired shape and elevation. So of course, you have already compacted the soil, but the compacted of the surface of the soil may not be very smooth. Okay, so in order to make that compacted surface of the soil more smooth and acceptable for further construction, then a process of grading has to be performed. So for the grading, then we have to use the type of equipment which are called as the graders. So this is a modern motor grader which has been shown over here. So finish grading or simply finishing involves smoothing the slopes, shaping the ditches, and bringing the earthwork to the elevation required by the plans and specifications. Okay. So we have, for this purpose, motor grader, grade excavators and trimmers. And then we have the estimating grader production. So grader production is usually calculated on a linear basis. That is the miles or kilometers completed per hour for roadway projects, and on an area basis, square yards or square meters per hour for general construction projects. So depending on the type of the product, so the production for the grader can be measured in terms of the miles per hour, or it may be a kilometer per hour, or in the terms of the square of the area per hour. That means the area represented in the square meters or square feet or square yard terms. So the time required to complete a roadway project may be estimated as well. So for example, the time needed for the roadway construction project it can be calculated like this. So it is the sum of the number of passes, number multiplied by the section length. So that means in the kilometer. So that means the number of kilometers it has. The grader has traveled, divided by the average speed for the section. So it's a very simple, straightforward formula multiplied by the 1 times the efficiency. Okay, so here we have the picture of a large grade trimmer, reclaimer, or paver. Okay, and typical grader operation speed is given over here. So if we have some different types of graders, then we can use the speed for using the formula which we have just described. So let's see how we can use this formula. So you can see that 15 miles, which is about 24.1 kilometer of gravel road require reshaping and leveling. You estimate that 6 passes of a motor grader will be required. So somehow you see that we will need 6 passes. Okay. Based on the operator skill, machine characteristic, and job conditions, you estimate 2 passes at 6.4 kilometer per hour, 2 passes at 8 kilometer per hour, and 2 passes at 9.7 kilometer per hour. Okay. So you determine that. If the job efficiency is 0.8, how many grader hours will be required for this job? So just apply this formula and then we can find it. So for example, 24.1 kilometer will need 2 passes divided by 6.4, that divided by the speed. So here you can see that the same formula has been applied. So that means we take this one at a time and then add it. So 2 into 24.1, 2 into 24.1, 2 into 24.1, and then at different speeds. The speeds have been already given, divided by the job efficiency, which is 0.8. So in this case, because you can see that in the previous cases, when we were using the job efficiency, we were multiplying it with the job efficiency, because in the previous formulas which we were determining, those one for the production. But here we are not finding the production. We are finding the time needed for the grader to work it on. So it is about 23.1 hours. So for example, if in this case, if we can plan that the grader will be working like 12 hours per day, so then it will take like two days to complete. If the grader will work like 8 hours per day, it will be like 3 days to complete this job. So in this way, we have determined the grader efficiency. Okay, so that one was some topic about the compaction and grading of the. So that was with this the topic is completed. So do you have any questions? If you okay.